Cut LLM latency and cost by half in Python. By the end, you will estimate token cost, model end-to-end time with batching, pick the heaviest prompts to prioritize, measure cache savings, and simulate simple parallel calls. You will get a repeatable mini toolkit you can adapt to any prompt set. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced in simple Python. Optimizing latency and cost targets two core metrics. The first is tokens per dollar, which ties directly to billing. The second is end-to-end latency, which includes per-request overhead and token throughput. The trade-off is clear. You can lower latency by batching, but batching can increase single request time and peak memory. Caching saves money on repeats, but uses memory and bookkeeping. At practical scale, small changes can save dollars per 1,000 tokens and shave seconds off user wait time. The intuition is simple. Count what you send, then model how long and how often you send it. Prioritize the big requests. Cache duplicates. Parallelize what remains. This approach shines on stable prompt sets and small to medium traffic. It does not replace production load testing, but it gives a fast, actionable baseline. We will build a compact analyzer that prints token counts, dollar estimates, batched latency, heavy prompt lists, cache savings, and a parallelism baseline for the same prompt corpus. This snippet estimates token usage and dollar cost for a tiny prompt list. It sets a per 1,000 token price in the variable rate and defines a simple white space token counter that never returns zero, so you never undercount. The snippet creates a small list of 3 short prompts to represent a tiny workload. It sums token counts across all prompts into a total and prints both the total tokens and a money estimate converted by the rate. If you increase rate, you simulate a pricier model and the dollar number scales directly. Lowering the rate models a cheaper model. The printed tuple shows how much text you will send and what you will likely pay. Now we will model wall time with batching and overhead. This snippet estimates wall time by grouping prompts into batches and adding per request overhead and token processing time. It introduces BSZ for batch size, TPS for tokens per second throughput, and O for per request overhead seconds. The list of prompts is chunked into batches of size BSZ. For each batch, the code adds the overhead once and then computes token time as the batch token sum divided by TPS, then sums these per batch durations into a total latency called LAT. Larger BSZ reduces the number of overhead additions, which lowers total time when overhead is significant, but it makes each request longer and can increase single request latency. Raising TPS lowers total time proportionally. The printed seconds show how long this workload would take end to end. Next, we will find the heaviest prompts to prioritize optimization. This snippet selects the largest prompts by token count so you can treat them differently. It pairs each prompt with its token count and then sorts those pairs so the largest token counts appear first. The snippet sets K to control how many top prompts to keep, and then extracts just the text of the top K items to highlight what dominates cost and latency. Increasing K widens the prioritized set so you pay attention to more prompts. Decreasing K focuses on only the biggest offenders. The printed list shows which prompts are responsible for most tokens, and therefore deserve special handling like rewriting, batching separately, or using a cheaper model tier. Next, we will estimate savings from caching duplicate requests. This snippet estimates costs saved by caching repeated prompts in the workload. It starts with a list of queries that intentionally includes duplicates. The snippet computes the base token usage across all queries and then builds a deduplicated sequence, using dictionary from keys to keep the first occurrence while removing later repeats. The difference between the base total and the deduplicated total is the token load avoided by caching. That token difference converts to a dollar amount using the same rate variable used earlier. More repetition in the query list increases savings, while fewer duplicates reduce them. The printed value gives a direct, practical estimate of how much money a simple cache would keep in your pocket. Finally, we will simulate parallel calls and balance work across workers. This snippet predicts latency when you run requests in parallel by greedily balancing tasks across a fixed number of workers. It sets C as the number of parallel slots and computes a per-request duration for each unique query, using overhead O and throughput TPS. Then it simulates assigning the longest remaining task to the least loaded worker repeatedly, which is a simple, greedy load balancer. Increasing C reduces the maximum worker load until tasks no longer overlap, while decreasing C increases the maximum completion time. This gives a small but practical baseline for how much concurrency will cut your end-to-end time after you already applied caching and batching. The printed seconds give an easy comparison point for different worker counts. Recap: this toolkit counts tokens to estimate dollars, models batching and overhead to predict latency, and uses prioritization, caching, and greedy concurrency to reduce both cost and wait time. Use it when you have a stable prompt set and want fast, low-risk improvements. One caveat is that this is a model and simulator, not a substitute for real throughput measurements under production load. Next step: tune batch size and number of workers while measuring real response times to find the sweet spot for your prompt mix. If that short, practical AI engineering helps, subscribe and watch the AI engineering videos.